All right. I'm going to introduce conservation of energy as expressed in the notation for the book that we are using. So we'll go through all the different terms here. First is the W on the far left-hand side is the change in energy of the system. That is the work done by external forces, so forces outside of your system. And it is going to be a zero if the system is isolated, because then there are only internal forces. Okay, so work done by external forces, left-hand side. The work done by external forces is what is going to cause the energy of the system to change. Obviously, if the left-hand side is zero, then the energy is constant. All right. What's on the right-hand side, the far right-hand side, then are all internal. Okay. If there is a change in mechanical energy, mechanical energy is the sum of kinetic and potential, then delta E mechanical will change. Okay? And all of our conservative forces that are internal to the system are here as potential energies, like a spring potential or a gravitational potential energy, or second semester of physics, a Coulomb potential. Those are all changes in potentials. All right. There is a change in thermal energy. So work done by friction. On this side of the equation, if it is a friction force that's internal to the system, it comes in as thermal energy increasing. So it's a plus sign. If it was an external force, it would be in the other side. And then the work done by friction would be negative. So what this term is trying to account for is, like, if I am rubbing my hands together, but that's internal to my system, my hands are getting warmer at the expense of some work done by friction, but it's internal force to the system. So I'm not accounting for it on the left-hand side. I'm getting there to be an increase in thermal energy due to the work done by friction. All right. And then last, there could be a change in the internal energy of the system. So internal energy is the energy that something has just by existing. So it could be the rest mass energy, mc squared, or the energy stored in chemical bonds, the energy stored in the binding energy of the nuclei. All of those things are contributors to the internal energy of the system. All right, so work done by external forces results in a change in energy. Change in energy of your system could be reflected in a change in mechanical energy, change in the thermal energy, or change in the internal energy. Most general form for conservation of energy that we're going to use for this class. All right, let's try some examples. So a rubber ball is dropped from a height h. The ball bounces off the floor, but it reaches a height of only 2/3 of h after the rebound. How can we use the principle of conservation of mechanical energy to interpret this observation? So think about what you think the answer is, and then compare with your physics friends. And you can unpause the video. We'll go over the answer together. All right, so it started with a certain amount of gravitational potential energy, mgh, hit the floor, and then bounced. After the kinetic energy is converted into gravitational potential energy again, you can see you've lost some energy because it only goes to 2/3 of h. Why? There were non-conservative forces that did work on the ball, and it lost mechanical energy in the process of bouncing. All right. We have a car driven along a country road on a dark and stormy night. Speed is 20 meters per second, so about 40 miles per hour. It's a horizontal and straight road. Driver sees that a tree has fallen and covers the road ahead. Panicking, the driver locks the brakes at a distance of 20 meters from the tree. Not very far. The coefficient of friction between the wheels and the road is 0.8. What is the outcome? So try to work that through as a example of using our conservation of energy principle, and then compare with your neighbor. Once you come to consensus, unpause the video and we'll go over the answer. All right, so the road is horizontal and straight. So we have kinetic energy in the car, which is going to be like a half mv initial squared. That kinetic energy is becoming final kinetic energy and then work done by friction to reduce the kinetic energy. Putting in numbers, initially I'm going to have, so the mass of the car doesn't matter, it's the same. No matter what the car's mass was, you get the same answer because every term is going to have a mass in it. So I have a half of 20 squared is going to be the specific kinetic energy initially. Specific just meaning I divided out the mass. The work done by friction is I've got 0.8 of g times the distance that the car can slide. Well, g is 10, so this is like 8. So I'm comparing a half of 20 squared with 8 times 20. So obviously I'm going to hit the tree. And then how fast am I going when I hit the tree? Well, the balance of the energy, in the initial state, it was all kinetic. In the final state, I've got work done by friction and the final kinetic energy. And you can work that out to be 9.3 meters per second. So definitely hit the tree. Can see that without really doing anything but thinking about the numbers in your head. And then working out a more detailed answer. You can see that the car is moving still at about 20 miles per hour and it hits the tree. Not good. All right. If the amount of energy needed to operate a 100-watt light bulb for 1 minute were used to launch a 2-kilogram projectile, what maximum height could the projectile reach, ignoring any resistive effects? So think about what you think the answer is. Work it out, and then compare with your neighbor. Remember, so this is a power of 100 watts. So that means it is using 100 joules of energy every second. Power is the rate that energy is transferred. All right, it was 300 meters, and we can see that as a 100-watt light bulb for 1 minute. That is 100 joules per second times 60 seconds. So that's the energy available on one side of the equation. So 6,000 joules, and making that up into 2 kilograms times G, which is, roughly speaking 10. So we're up to 20. And then to get that to equal 6,000, it's going to need to go about 300 meters.